Hey guys, we're gonna get started. If you don't mind taking a seat. If you don't mind taking a seat, we're gonna get started. So, thanks once again for coming down. Today we have a great topic on, by back from GridGain and developing from MapR. It's going to be a great topic on, in-memory computing in NoSQL, meaning Hadoop. Before we get started on that, let's do a few announcements. So we have the Spark Meetup next Tuesday at DirecTV. If you're interested in joining that, go to the Meetup page and register for it. Also, December 1st is a holiday party meetup. If you guys have signed up, well and good. If not, there's more information on the Big Data website about it. We have on December 4th, Alan Gates, one of the co-founders of Modernworks and Hadoop, will be coming out to give a talk on Stinger.next. December 11th, still working on the details, but it's almost finalized that the guys from Databricks are going to come down and give a talk on Spark. January 15th of next year, we have, we're going to get into the mood and get Hadoop out the door. So we have a Hadoop in the cloud, debugging with Hive session with the guys from Artiscape. December 27th is also another great topic with the guys at DataMere talking about, their solution of, how do we integrate with Hadoop as well as do analytics on top of Hadoop. February, we have two great meetups. We're going to have an HBase committer come down to give a talk on HBase and also another Spark talk in February. So, great lineup of talks. We're posting a lot of these information on the website, so keep track of it and watch for it. Before we start, I want to invite Cordero from GridGain to give a few minutes of talk on GridGain and what they do. So let's give a hand for Cordero.
I like being up on the stage. Testing, can everybody hear me? Testing. I probably don't need this because my voice definitely does boom. But I want to thank the Los Angeles Big Data User Group for hosting bringing this event together and allowing us to come out and present to you guys. My name is Cordero Brunel from GridGain. I am the Director of Operations for Central and Western regions. We're here today to talk to you about our in-memory technologies and what in-memory technologies are doing out there with the world of real-time access. Real-time access is different to a lot of people. It could be microsecond for some people. It could be days for some people. And so GridGain has been around since 2007 as an enterprise. Started as a garage project. Our two founders are still active in the company. But we are completely focused on in-memory technologies. So those of you that are having data performance issues, we are a solution to that. So we have customers that, yes, are big data, that have petabytes, hundreds of terabytes of data that they're storing in memory. And then we have the common customer that's got gigabyte levels. So for us, it's not necessarily the data size. We can handle any variant thereof, but it's truly about data performance and getting fast access to your data. So hopefully everybody's familiar with in-memory technology. If not, I'm here with my solutions architect, MapR, who will take you through that. If you didn't sign up already, we're going to be raffling off a Jawbone Jambox, pretty cool Bluetooth speaker. So if you haven't registered, please register at the door. And if you have any questions, see us afterwards. If not, I hope you enjoy the presentation.
Thanks, Cordero. So I'm going to invite MapR from GridGain to come and talk about the in-memory solution. One last thing about GridGain, just yesterday they open source your product. So if you're interested in taking a look at what they're doing, it's an Apache, right? You can go and just grab the code from Apache, play around with it. So without further ado, let me get Mac to come and talk. Mac.
Thank you. Am I on? I think I have my last one. Okay, good. So thank you. Yeah, don't steal my thunder. The Apache thing is like 5 slides in. So thank you guys for coming. I'd like to echo what Cordero said. Appreciate you guys for having us out. This is a great venue. Thank you guys for coming tonight. So let me give a couple of thoughts up front. I love to kind of keep these things interactive, although the lights make it feel a little bit formal. So, we're not that big of a group. So if you guys have questions as we go through, please ask. That being said, I do have plenty of time to chat with folks afterwards too. We do have a fair amount of material to get through. But if there's some burning questions, throw up your hand or shout it out and be more than happy to go through those. So again, yes, my name is MapR. I'm Solutions Architect here at GridGain. I've been working in the in-memory space for several years now. Before that, my background was perhaps similar to any of yours. I used to work in IT, was originally a developer, and then ran development teams and was kind of the director when I left that world. So if you are evaluating technologies right now and trying to solve problems, that's sort of what I'm very familiar with and what I get to hopefully help folks like you guys do in my role here at GridGain. So what are we going to talk about today? We're first going to talk about in-memory technology, why it's important, what some of the key use cases are, how some of these architectures have evolved, what are the key concepts, what are the considerations. If you're looking at any of these technologies, right, not specific to ours, of course, I hope that you'll be interested in what I have to say about our product, but we're going to start generic, right? If you're looking at any of these types of technologies, what are the things, if I was a customer, as I've been in the past, what are the things I would want to think about? And then after we get through that piece, we'll talk about specifically GridGain's approach to these things. So we're going to kind of talk about some problems and approaches in the abstract, and then I'll tell you how we do it, how we solve it. And that includes the data grid, the compute stuff, streaming. We have a Hadoop product, and of course, I'm sure many of you are interested in that because Dale's here from MapR. And we've been chatting about the possibility for us to work together as well in the future. So we'll cover all that stuff. I'll point out a few things that have happened recently in our latest couple of releases as well. So let's jump right in here. First of all, let me ask, is anybody already using in-memory technology, caching, data grids, any of that kind of stuff? So how many of you, let's do languages. How many of you work primarily in Java, C#, guys, C++? What about Python or R, other stuff like that? Okay. And how many are using Hadoop today? Some people, and I assume a lot of you are thinking about it. So thank you for that. Helps kind of know what we're talking about. So why in-memory computing? First of all, speed, right? Traditionally, if you think about the architectures we've all had for years and years, we have application servers, Java or some mix of other languages, we have data in databases. All that data lives on disk. Depending on the numbers that you want to go with, there have been many published, but RAM is typically several hundred to several thousand times faster. That's kind of the fundamental principle, right? Obviously, there's a lot more to it than that, but fundamentally, it's performance number one. You have the big guys on the consulting side saying things that are fairly bold. They don't tend to talk like this every day, but disruptive impact, massive potential, et cetera, et cetera. In fact, Gartner has gone so far as to say that, went too far, that those that do not adopt in-memory technologies might be out-innovated by competitors that do. So fairly bold statements. I'm not here to talk about hype. I'm here to talk about technology. so I won't belabor that point too much. But the trends here are obvious, right? I mean, number one, and we kind of all know this, our data sets are growing year after year, right? Hopefully, you're gaining more customers for your companies, you're gaining more data. That becomes an increasing challenge, especially as we try to maintain performance. The thing that works in our advantage for those of us in the in-memory space is RAM has continued to get cheaper and cheaper as the years go on. So that sort of sets the stage, gives us that ability to deliver these types of in-memory solutions that can really hold massive amounts of data and can do it cost effectively. So let's, as I was saying, kind of talk in the abstract first, right? If I'm thinking about in-memory computing at all, first of all, why would I be thinking about it? So here, kind of my take on the topic we're using. Number one is performance. We already touched on this, right? Maybe I can't meet my SLAs. You know, if you've been through the progression that I've been through to build applications and scale, you know, the first thing you have to do is I need to add more app servers. And the next thing that happens is my database is the bottleneck. So what do? You build a bigger box. And then at a certain point, that's not enough. Where do you go from there? So maybe I can't meet my SLAs. Maybe I'm trying to build a new class of application that just isn't possible with the speed that so performance is important. We'll talk more about that. Number two, scalability, right? Can I just escape this database in a box idea? Can I scale out horizontally? Can I do it cost effectively? And number three, future proofing. So if I can do those first two things, that should give me sort of a roadmap to move forward. Right? I know that I can handle fast data at any scale that I need, and I can do it cost effectively. So I know no matter how much data I get or how many customers, how many users, etc., I have a platform that I can go forward. So what's the basic idea here? So again, let's think about our traditional architecture. Right? You have application servers, you have databases. Typically, app servers have been fairly small, right? You can't necessarily hold a lot of data in RAM in the app server. You think, maybe not so much today, but maybe a handful of years ago, your average app server just didn't have that much. Right? So you have most of your data in a database, and I have a little bit of data in RAM, but you kind of just funnel little bits in there, and I work with them, and then they're gone. The idea of moving to in-memory as a concept is really about flipping this on its head, right? So we're not getting rid of the database. That's still going to be there. We have all these lovely processes for ETL and backup and recovery and all this stuff, so we don't necessarily want to lose that stuff. But we don't want to necessarily depend on that for our performance. And what we want to do is move a whole bunch of data into memory on those application servers or on some other servers that are going to sit beside the app servers. And it's not just one. So the key is I'm not building a big box again. I'm building a distributed solution, right, that runs on lots of boxes that can hold any amount of data that I need in memory and deliver it very quickly. So again, why? Right? Why do I want to do this? Well, these are some of the more common use cases. Obviously, this doesn't encompass every vertical, but financial, for example, has been a real big adopter of this type of technology. You know, you think about processing market data. You're a hedge fund, you're the trading desk at a large bank. Maybe you're a software vendor in this space, and those are your customers. But you think about dealing with market data feeds, and you think about having dozens or hundreds of traders with dozens of portfolios, which may have thousands of positions, and you need to recompute all this stuff every time the market flips. It's a massive problem, right? And you have to do it very, very quickly. So this really lends itself to in-memory. It lends itself to distributed computing as well. Another aspect of that is risk. If you're in charge of processing a credit card payment, or maybe more exciting and more relevant at this particular moment is mobile payment, right? How much time do you have to make a decision if you're going to approve or decline a payment? Maybe a second. Maybe somebody standing there, they're waiting for that to happen. So those have certainly been great use cases for this type of technology, but also things completely different, where you're going to see some common threads even though for different use cases. Online and mobile ads, right? If I have to serve an ad to somebody, they're loading a web page, they're firing up an app. How long do I have to pick the ad? I have people bidding on this space. I have some algorithms that are going to determine what's the right thing to offer to the person, and I have to do that very, very quickly. And then I want to track how they respond, and then my managers probably want to see how people are responding in real time. Or even sort of customer 360 views. I want to look at customers interacting with my system in real time. So there's lots of different aspects. The common themes are around velocity, volume, and real-time performance. So the performance thing is always there, and then sometimes it's large data, sometimes not. Some customers maybe gigabytes of data, others terabytes, or in the case of Hadoop, maybe it's petabytes. So with that little bit of background, again, thinking about these traditional architectures that we've all been building for years and how things have changed, let's go through a few steps here. So first of all, let's kind of break down the traditional architecture, right? So I have app servers, I have databases. Now you might have a service layer in the middle here, but we've simplified this by just keeping it to the two. Think about how data moves in this system. You know, I have application servers. They're actually doing work, users are interacting with stuff. They need relational data. All that data lives on disk, right? So that's a limiting factor right there. I'm going to ship relational data across the network to an app server. Once it gets there, I got to convert it to objects, and then I can actually do something useful. So that's the way it's been, right? Obviously, what's your central bottleneck? It's the database and it's these goods. Now, the next thing that you might say, when I've added more app servers and this has become a problem, is you might say, well, gosh, wouldn't it be great if I could just make the database bigger, right? So, again, as I mentioned earlier, the first thing you can do is build the biggest box you can afford or want to spend the money on. From there, well, a lot of times with a lot of boxes, you're kind of stuck. Now, you might be able to upgrade to one of these horizontal scalable databases. These tend to be analytical databases, things like vertically pizza, right? Very, very expensive. Have their own set of limitations. It can improve performance if you can afford it, but if you think about that data movement, again, it really doesn't fundamentally change the picture at all. I'm still shipping relational data across the network, I'm converting it to objects, I'm using it, it's all still disk-bound, and so on. So what's the next step? Well, the next step for a lot of people is to move to distributed caching. And this is one of the things we can do, although we can take it a step farther, which we'll see in a couple of minutes. In a distributed caching world, I introduce another product here, a data grid, right, that can store data in RAM on commodity hardware, hopefully cost effectively. And I go get data from there if it's available, right? So I put as much RAM in there as I think I need, and I store data there as I need it, right? So it's kind of put data in this grid and let it live for a certain period of time or refresh it on a certain interval, that sort of thing. So this dramatically improves scaling, right? Orders of magnitude in many cases. 5x, 10x, even 100x if you're lucky, is certainly possible. So now I've got data in memory, it's very, very fast. I still have to ship it across the network, but I'm storing objects now. So most of these solutions, and certainly ours, store objects. Right? So once it gets there, I don't really have to convert it, I just use it. But I am still doing the processing, you know, on that node, I'm still moving data across the network. So huge improvement, but you can actually go even further. And this is not the only deployment that you can do with GridGain, but I pointed out because it's the most different looking deployment, where I can now sort of collapse this model and say, let's just have a whole bunch of nodes that I can throw more boxes at this cluster at any time. I can run my application server, I can run the data grid, and have it all integrated. It's all in memory, it's all local data, it's all objects. It doesn't get much more than that. And we'll go into a lot more detail about how you can deploy and what our technologies look like. But this is kind of the idea. You kind of see how there's hopefully a series of steps that get us closer to optimal performance. You know, once I'm dealing with data local in memory on a box, you can't really get faster, right? I mean, where do you go from there? So if you're thinking about these types of projects, you know, again, not specific to ours, but what are the things that I think you might want to think about? Number one, of course, performance. There's a handful of others. Scaling, right? How does it scale? Consistency, we'll talk about what we mean by that if you're not familiar with the term, but this is something where you'll see a lot of differences in different products in these areas. Persistence, right? If I'm storing data in memory, obviously that's volatile, so what are the options to persist the data? Can I support transactions, right? The same way that you would in a traditional database. Some products would do that, some would not. And how do I search that data? How do I query it? So let's break those down real quick. From a performance standpoint, you know, this is really a situation where you have to understand what performance means to you. Right? What is my performance requirement about? Is it about doing things in real time that right now take hours? Is it about meeting a certain goal for throughput? Is it about cultural latency? Is it about maybe keeping the performance that I have today, which is acceptable, but with a much larger data set and being able to scale it? You know, so those are the things you would want to understand as you start this journey. The next piece is about scaling. So how do, if I look at a product that can store data in memory, how does it scale, right? Does it scale horizontally? You would hope that most products would. But can you do it without downtime? Can I add a brick to speak anytime I want? Or do I have to sort of restart everything or have downtime to do that? How much memory can I use with a single process, or can I use all the memory on the box? Does it have good monitoring? How do I understand how well my nodes are being utilized and how many data is being utilized? So those things are important. Consistency. Now, when we talk about consistency, we talk about weak or strong models, eventually, or strong consistency. Does everybody know what I mean by that, by the way? Some people do. So if you're not familiar with the term, if you think about a data grid where I have data on lots of servers, right, and the possibility exists in many architectures where a particular piece of data might live on multiple boxes, maybe dozens. So the consistency question comes in then, if I have data where the same data point lives on several boxes, can I change it? Is there a possibility that, during or right after that change, somebody might ask a question of one of the boxes that's holding that piece of data and get an answer that's not the thing that I just changed, right? So is there a possibility for stale data? So when we say eventual or weak consistency, there is a possibility for stale data within a certain window of time. In a strongly consistent world, there's not. You're guaranteed that if you change something, the next time somebody reads it, no matter how close in time that is, they're going to get the same answer. And no matter what box they ask for that answer. And then from there, okay, maybe I have these different models, but how granular is it? Can I use different models at the same time? Can I configure it on a per store, per cache basis, or do I have to do it globally? And then the last point is really important. What's the impact on performance of these choices? And I guarantee you there will be impact of those. The next piece is persistence. So are there flexible options? Can I persist how I want? Can I read through, write through to a database? Can I use shared storage? Can I write through a file system? What are the options there? And then similarly on transactions, right? First of all, can you even do it? Is it simply a local transaction like in one box, or does it span the whole grid? And again, can it be configured granularly, or is it global? What's the impact on performance? So those are things that are very, very important. If some people need transactions, but they need to be able to depend on that data, even though it's in memory, depend on it the same way they would in a database. Some people don't. And last but not least is search, right? So different products will give you different methodologies in terms of how to search data. Do you have some proprietary API that you have to learn how to search, or can you use SQL? Again, what are the options? Can I index it? Where are the indexes stored? On disk, or the indexes in memory? Is there a JDBC or a DBC interface? That's obviously if you did SQL, you would also want to know if you have to have a look to the API to issue a SQL query, or if I can just do it through standard interface. So with that kind of brings us to the piece where we'll talk a little bit about GridGain. Any burning questions on what we've said so far?
I want to ask a little bit about this, because you sort of presented them all as gifts.
Mm-hmm.
What I see a lot of the applications is moving aggressively towards solid state,
Sure.
and having technology to kind of automatically monitor the temperature data and
Okay.
ship it in and out back and forth. And so, I see them kind of pursuing that. If the solid state offers a great price performance, a lot of using kind of RAM and
Sure.
things. How would you?
So good.
What would you say the impact of that is on kind of your approach to going all in for RAM?
Sure. So good question. So we'll talk more about this a few slides later as we start to look at the data fabric and where that sits. But the short answer is, we tend to sit between whatever underlying persistent stores, whatever databases you want to use, and the applications that consume that data. So as such, we're fairly agnostic to what you want to use on there. You want to keep your Oracle and SQL Server, that's fine. You want to use something else SQL, that's fine. And if you want to use spinning disks or SSDs, again, that's fine. We don't really care. I would put it in perspective by talking about orders of magnitude. So if you use performance of, let's pick on SQL Server on disk as a baseline, and then I say SQL Server on SSDs, it's probably an order of magnitude, probably about 10x. Right? And then you look at an in-memory solution, another order of magnitude, 100x fast or more. So we see that as absolutely a useful piece of the puzzle. So if you have data in disk-based databases and you can afford to go SSDs, we absolutely recommend it. We're going to provide the next order of magnitude performance on top of that. And we're never, well, maybe not never, but we're rarely going to go in and say, let's take everything you have in your disk-based systems and put it in there. It's really for us about the hot set of data. And we have a tiered storage strategy as well, but ours is all within memory. So we have heap and off heap and talking about that. So that's kind of a good segue as we start to kind of touch on some of these things. Let's talk about GridGain. How do we approach these things? I brought up some questions, right? What are our answers? Use cases, you've seen this slide already. You get to see some of our real customer logos up there now. We've won some cool awards that we're pretty proud of. Don't need to belabor the point, but obviously Gartner, for example, is pretty exciting to us. Also exciting was a particular use case I'll just mention real briefly as a good example of the kinds of things that we're able to do for customers. Sberbank, one of the largest banks in Europe, had a very competitive bid for a solution within their trading operation where they wanted to do a very specific test, with very specific parameters, and this is what it looked like. They wanted to be able to achieve 1 billion transactions per second, essentially updates, writes, within a transactional context. And they wanted to do it cost-effectively. So what's a solution that can help me do this in the most cost-effective way on commodity boxes? So we were able to do that for them. 10, those are standard 1 UDEL boxes, right? Those are not, there's even a newer model than that. So if you wanted to buy the newer model, it's probably less than 40K. If you actually bought those today as refurb, it's probably less than 25K. But 10 servers, terabyte of memory, billion transactions per second with our software. So that was pretty exciting. And definitely shows you, a terabyte, and again, at the refurb price, 25K, very cost effective. One more thing while we're on this, and then we'll dive right into the architecture. As was hinted earlier, so very exciting for us, just in the last couple of weeks, we've been accepted into the Apache Software Foundation. So our open source, we have both open source and enterprise software. I'll point out the differences to you towards the end, but suffice it to say, all of our core functionality is available in open source. We have security, manageability, that kind of stuff in enterprise, but all the core stuff is there. That's going to now become a project called Apache Ignite. So that's something that we're very, very excited about. So our model will be somewhat similar to some of the others in this space. If you think about Cassandra, you think about even Hadoop in some cases, where there's an open source core project, and then we're still going to have enterprise services and support on top of that. Good. So here's the big picture, right, of the actual architecture. A couple things to say first. First of all, we are Java-based software. So like Hadoop and some of those other things we run in JVM, as you guys know, that means we can be deployed pretty much anywhere. Your own hardware, VMs, private cloud, public cloud, all that stuff is fine with us. And although obviously we have very robust support for Java because that's our native platform, we also have very rich support for .NET, C++, and we do have a SQL interface, so we'll talk about all that stuff. But there's basically sort of 4 functional areas, which are these guys here. So we have our data grid, our clustering and compute capabilities, our streaming capabilities. Those 3, from a code perspective and from the perspective of you going to download it, are really one product. It's primarily just what APIs you choose to use or not. And then we have our Hadoop Accelerator, which is a little bit of a standalone piece, although it actually is built on the same technology, built on the same platform, but kind of a standalone. So if you were only going to use Hadoop, we'll explain that to you. You wouldn't necessarily have to understand or care that these things are at all related. So let's start with the data grid first. Again, we talked at the beginning about things that you would consider if you're looking at these types of products. I'll start with the similarities between us and many of the others in the space. First of all, we are an in-memory key value store, rate distributed key value store. If you're familiar with map operations, get, put, remove, right? These are the basics of a caching API for pretty much anybody. And that's true for us as well. We support multiple different types of data stores or caches, so local, replicated, partitioned. 90% of the time, if you're looking at this type of product, you're looking for partition, and that's what most people are going to use. What that means is my data is spread evenly, across these nodes in my data grid. So every node holds some of the primary data is some of the redundancy data, right? So we have HA, we have multiple copies of the data, memory, and so on. In terms of scaling, just some anecdotal numbers, right? How large can you go? Things we've seen customers do. We have customers doing, certainly on the low end, gigabytes of data, but they just need really fast performance. On the high end, dozens to a few hundred terabytes of data in memory. There's no theoretical limit, but that's about as big as a cluster as most people have thought. And again, it's about that hot data set. So you may have terabytes or petabytes that you've got to do of data in your system in total, but what is the subset of data that your apps really need on a daily basis, that you use for hammering all the time? That's what we would put in the grid. If you're compute heavy, and we'll talk more about compute in a minute, on the high end, I've seen customers testing upwards around 1,000 nodes. For example, Squarebot did that just to see how high they could go. That was about as high as they felt like going, and it worked just fine. So you can certainly talk about large data sets, but it doesn't necessarily require a large data set for this to make sense, right? It just requires data that needs really, really fast performance, and applications that want to consume that really, really quickly. So let's talk about some of the differences now. First, as you guys know, those of you that raised your hand and have worked with Java, if you want to scale, and you think about scaling up on a single box, what's your limiting factor? I want to use lots of RAM on a box, increase my heat, without running heat. So the only solution for that is to have off-heat memory support as well as on-heat, which we do. And what that practically means is you can run a reasonably sized heap, which to me means about 8 gigs. And let's say you have a 128 gig box. So I can have an 8 gig heap, I can use 120 gigs of off-heap, use all that memory with a single process. Now in reality, you leave some overhead for that. You guys know what I'm saying. The important point there is if you're looking at different approaches to this problem, if you did not support off-heap, your only option would be to run dozens of instances to use all the memory on that box. So even with a handful of boxes, suddenly you may be running upwards of 100 instances, right? It becomes really difficult to manage. With off-heap, if I have 5 boxes, I run 5 instances. It doesn't matter how big the box is. So that's really, really useful. And the horizontal scaling piece, which we talked about earlier, add a brick for us, is done without NAPL. So I can add nodes, make this grid as big as I want, whenever I want. No downtime, no outages, doesn't lock the world. So you need more storage, you need more compute, throw more boxes in the grid. We talked about the redundancy, right? So we have HA, we have multiple copies of the data in memory. We do support strong consistency, which I brought up earlier, at all times. So whereas some other vendors won't give you strong consistency at all, or maybe they'll give it as an option, unfortunately, with most solutions, if you turn that strong consistency on, you're going to take a huge performance. Luckily, we do not. So we were architected with that approach in mind from day one. We have a multi-version concurrency control pattern in our architecture that allows us to do strong consistency, to do it very, very quickly. In fact, we'll outperform most of the other solutions, even running in eventually. So that's good stuff. And we do also support this. So if you need transaction support, you can do that. Optimistic, pessimistic, different isolation levels. That's all configurable with us. I did mention SQL query support, right? So you want to query the data, you've gotten it in through the APIs, now I want to search it, I want to query it. You can do SQL. If you're a Java guy and you've ever looked at HQL, you know what it looks like. It looks like standard SQL select, but I'm selecting, in our case, from a cache. In fact, you can even join across caches. Question?
What is the SQL 92, or is that including window functions?
Basically 92. Yeah. We're expanding that over time, but the initial focus was on reporting analytics type issues. So it's basically the read stuff that we do for reporting. But I've seen people do some fairly hairy stuff in terms of like nested select, sub-select, unions, that kind of stuff. And again, the cross-cache joins, which as far as I know, most of the other products, maybe all of them, can't do. And then the last point I want to emphasize, and that'll take us into the next piece here, which is the compute, right? So there are products in this space that kind of just do this piece. They do the caching, that's it. Obviously we know who our competitors are, we test heavily against them. We're more than happy to go head-to-head in a performance battle with anybody just on this feature set. But if you start to move outside that feature set, this is where our proposition, I think, is really unique. We have a lot of other functionality, right? So compute, for example. compute has been a part of our platform from day one. It's not something that we tacked on as an afterthought. It's something that was there. Our original background of our founders was in building distributed compute things. So again, it's been there since day one. There's a really, really rich API for compute. It's the idea where I'm running tasks in the grid. Like from a practical standpoint, I'm running closed grid, probably those kinds of things. Lots of patterns that we can support. We can support MapReduce patterns. We have lightweight messaging. If you wanted to do API and compute file apps, we can do that stuff. Typically, we're talking about event-driven apps, right? So I'm triggering tasks in the grid based on things that are happening in the system at that time. But if you have things you need to schedule, right, we can do that. So we have the promise files, scheduling syntax if you need it. As you think about tasks running on different nodes in a big grid, the things you would expect are going to be there. If I need to share state between different tasks that are executing, I can use the session construct to do that. Because we're providing resource management and high availability, if the task is running on a box that fails, we'll move it. If you want to checkpoint the progress of that task periodically and it does ever have to move, we can pick up where it left off. Another problem that you run into as you think about executing things in a grid is during development. You know, if I'm sitting there writing code in my IDE and I want to run it in the grid, say, I've got my laptop and I'm developing, and then I have 25 nodes over here to play around with. How do I go from here to here? Like, do I have to build a jar and copy it to 25 places? That would be painful if I had to do that every time I change a line of code, right? So we have a solution for that as well. That's the zero deployment technology where we can send those tasks across the wires. Again, if you're talking Java, we're talking about closure monitors, that sort of thing. We can send those processes across the wire on the fly. So you're not building jars, you're not copying stuff. Now, in production, if you wanted to turn that off and use a managed model and force deployment, you can certainly do that. The last piece I want to emphasize here, too, the pluggable SPI design. This is really true for all of our products, although we have to do it on the compute side. One thing that I really like about GridGain when I'm developing one is this idea that A, it's very configurable, but B, more importantly, I think it's extensible. So we don't want you to be in a situation where you're kind of stuck with certain behavior because we never thought of it. You're going to run into things and have your own unique requirements, and that may include things that you would have never heard. Right? So we have 14 or 15 different subsystems defined that govern different aspects of our behavior. Things like discovery, indexing, load balancing, etc. Where we will give you 2 or 3 implementations out of the box. But if you don't like one of those, you can write a little bit of code. That SPI is a service provider interface. It's a fairly lightweight interface, as lightweight as we can make it. Write a little code, plug in your own behavior. So for discovery, for example, how do nodes find each other? So we'll give you a multicast option. We'll give you a direct TCP option where you list IP. If you're using Amazon S3, we'll give you an option to use S3 buttons. But if you don't like those, and I don't know why you would do this, but as an off-the-wall example, maybe I say, oh, use LDAP for node description. Well, you can write a little code and make that happen. So let's kind of bring these concepts together. If you go think back to when we talked about distributed caching as a concept, right? That's kind of this picture here. And again, GridGain can do this. If this is what you want to do, we're more than happy to do it. But we see this as kind of step one in the evolution. Again, so here we were on an application server, right? I'm going across the network to request data. In this case, I'm getting it from data grid, so it's in memory, it's faster. But I'm still shipping across the network to bring it back to the app server to work on it. GridGain can take you to that next step, where you're turning that pattern around, and I'm going to send the compute out to the nodes to work on in-memory data and return the results. Those of you that are doing Hadoop or looking at Hadoop, you're familiar with this concept, right? This is not a foreign idea here in this day and age, but when we started talking about this several years ago, before Hadoop sort of entered the popular consciousness, it was a somewhat unconventional idea at the time. Nowadays, I probably don't have to tell you why it's valuable, but as data sets grow, you think about having to ship data across the network, that's going to become the bottleneck, right? If I don't have to ship that data around all the time, then I don't have that problem. A couple of other quick things. So we do support a number of structures, and we're talking mainly about Java because we're Java-based, but I will talk about the other languages briefly towards the end here. So obviously we have map type operations covered, right? Cache is that plus a whole heck of a lot more. But we have things like queues, countdown latches, atomic ones, that sort of thing. These things that tend to become helpful as you're building distributed applications. You may never need them, but if you do, it's there. The last major bit of functionality, if you think back to that big diagram with data grid and compute and streaming, which was the third piece, what did we mean by streaming? So what do we do there? We really mean two things. We see more and more customers that are doing these types of things, where they're trying to ingest data at real time. If you have market data feeds, obviously it's a streaming problem. If you ingest social media data in real time, obviously that's a streaming problem. But even in some of those other cases, like Customer 360, where I have different interactions via my website, via my mobile app, via my call center, and I want to look in those interactions as sort of an event stream. Whatever the data is, we think you need to do two things. Number one, process, keep up with the flow. Right? Typically, the events need some minimal processing, filtering, cleanup, enrichment with metadata, whatever the case may be. So we help you build workflows. You define a series of steps in config, and then you implement those in code. It can be as simple or as complex as you want. But those workflows then execute on the grid, so that makes it very easily scalable. And once you've done that, I'm ingesting the events very quickly, I'm keeping up with the flow. Then I also want to be able to do analytics on those streams in real time. And that's the second half of the functionality. So first piece is workflow, second piece is analytics. So we have API support for this concept of sliding data windows. You can have as many as you want. Typically there's time bound, 15-minute window, 2-hour window, 24-hour window. As events come in, the data gets indexed, and when you hear me say that, that means it's an in-memory index. And then you can do continuous queries, right? Sort of predefined queries, look for events that meet a certain criteria, deviate from the moving average, exceed a threshold. Or you can do ad hoc queries after the fact as well. And the key is, when we find an interesting event, you get a call on it. So I can execute arbitrary code, I can notify you, put it on a dashboard, etc. So with that, I think we've got about 10 minutes to go, because I don't want to eat into Dale's time. That brings us to the here. But any questions on these pieces? Real quick. So far, so good. So Hadoop, what do we do here? So as I mentioned, this is kind of a standalone piece, right? So if you're looking to accelerate Hadoop, we can help. And what we do there is provide an in-memory file system that becomes the caching layer on top of HDFS. So in this diagram, you see the orange pieces, the darker orange is something supplied by GridGain, the lighter yellow is sort of standard Hadoop components. What we're showing here at the bottom is a GridGain file system. In-memory file system, it can sit on top of HDFS. That's going to be the use case for 90% of our customers. In theory, it could stand alone. We don't actually force you to have HDFS underneath it. That could be interesting for a small real-time use case, but typically you have HDFS because you have massive amounts of data. So in that case, we go back to that conversation about hot data set. Right? Maybe I've got petabytes in there, but what is it that my customers are hammering on, or my users are hammering on day after day after day? Maybe it's this quarter's data, this month's data, this year's data. Let's think about accelerating that by putting it in memory. So the way this works is you download our software, no matter which product you're downloading, whether it's Hadoop or the others. It's essentially a big zip file, right? It has a configuration file. You run the start script. In the case of the Hadoop accelerator, you would run this on your Hadoop data nodes so that we can grab memory on those nodes and preserve the locality that Hadoop expects. So you've got a GridGain process running on your data nodes. We've got memory we can use, and then you configure us, say what data in HDFS do I actually want to cache, right? So it's a file system. So you're saying what files, what directories, you can use regex patterns, etc. But you're telling us what's important to you, what do we want to cache. As you access data through standard Hadoop APIs, right, we're going to go to HDFS once and get it, load it into memory. We're using data grid technology under the hood, but again, you don't necessarily need to know or think too much about that. We'll cache as much data as you've given us space. We cache Hadoop at the block level, right, so it's blocks of data, pretty granular. We'll try to preserve the hottest blocks. If we fill up that space, we can evict the coldest blocks with some intelligent eviction. And if we need the data, we'll go back to HDFS to get it. If you change the data that's in memory, you can push those changes back to HDFS either synchronously or asynchronously. That's your choice. And if you request data that you've told us not to cache, we essentially just sort of proxy that call straight through. Go to HDFS and return it without doing anything further. This does work with any of the major Hadoop distributions. Because we sort of plug in on this layer that sits on top of HDFS, it's a very straightforward thing. So we're not specific to any distros. You can use any of the ones that you like. Now, I should probably back up. So there's one piece I didn't explain, which is this. So we have an in-memory MapReduce acceleration as well. This is an optional piece, right? You could just use the file system by itself. But if you have a particular use case for MapReduce, where you're trying to run MapReduce tasks in very, very low latency sort of time, you have a MapReduce task and you're going to execute in a second or a sub-second. You'll find that there's enough overhead in Hadoop that it's probably going to take you 30 seconds to even spin up a job, right? And it's no knock on Hadoop. It was architected for resiliency, redundancy, batch operations originally. So there's all these different processes on different boxes. They all have to talk, and then name node, job tracker, task tracker. Eventually, it'll spin up a new JVM on a job. That's all just going to take some amount of time. So if you have a job that's going to run for hours, you may not care. But again, if you're trying to run a MapReduce job in a second, waiting 30 times longer for it to start doesn't really make a lot of sense. So that's where we can help. We have a MapReduce acceleration we can plug in under the standard API. That does require Hadoop 2 and Yarn to make that pluggability possible. But we can plug in, and what we essentially do is cut out all these different moving pieces and parts. So if you're already running the GridGain file system, right, that's the assumption. So I'm already running GGFS. I can essentially make use of the topology that GridGain provides to send tasks directly to those data nodes without consulting a name node, without spinning up new processes. It's now a point-to-point connection between two always running processes. Very, very fast. That's how I can do MapReduce in sub-segment type of time. So if you have that particular problem, that's something that we can help with as well. But again, it's an optional piece. All you need to do is accelerate file I/O with that caching layer, and you can do that, and not necessarily have to do anything further. So in the last few minutes here, a few other things just to make you aware of. Monitoring management to me with any software product has always been a really important piece. Our tool is called Visor. We put a lot of work into making this the best tool out there, certainly in our belief. So let me briefly tell you what's in there. As you can imagine, kind of on the left here, you'd have the dashboard when you first launch the tool. You'd see all the grid nodes, performance metrics. It gives you the ability to start, stop, and restart nodes, to drill in and look at an individual node's environment or configuration. But more importantly, depending on the functionality that you're using, we have lots of different screens, more than I could actually fit on one slide, which is why we have really small screenshots, and I apologize for that. But depending on the functionality you're using, there's screens dedicated to it. So for streaming, it's this guy here. You see different streaming stages that are executing in the grid. What nodes are they running on? How quickly are they executing? What's the throughput latency? For caches, you'd see, here's all my caches. How many objects? How much memory? What are the hit ratios, read-write ratios? What nodes are participating in these caches? All this kind of stuff. And if you want to write SQL queries to query that data, you can do that right there in Visor. If you're using Hadoop, we have a file system profiler, so I can see on a file-by-file basis what's the performance I'm getting in memory versus on the HDFS file system. So that's kind of the product. Let me quickly tell you about a couple things we've added real recently here. 6.5 was our latest release. In 6.5 and the release prior, we've really filled out our cross-language capabilities. So very, very robust support now for .NET and C++. You can do pretty much all the things in .NET, for example, that you could do in Java. You can run a near cache, which we didn't really talk about. But if you want to run, caches on the application server separate from the grid, so things they request frequently, I can store locally on the box. So if I need that data, I don't even have to go across the network. You could always do that in Java. You can now do that in .NET as well. And while we're on that subject, just to give you sort of order of magnitude, if I have to go to a database and get data, you think about how long it takes to run a SQL query. You're probably talking a couple hundred milliseconds, maybe, or more. You think about getting data from a data grid where it's in memory and you're going across the network to an in-memory software product, you're probably talking 4 or 5 milliseconds. If you have a near cache enabled, you may be talking a microsecond or even nanosecond of access to that data. So it can make sense in some cases. So you can do that, again, in Java. You could always do that in .NET and any other languages. You can do that now too. we have, the big piece we have here is what we call grid portable objects. So one of the big problems you run into if you try to do this is, well, how do I actually store the data, right? Fundamentally, if I was storing Java objects, how do I use that from C++ or from .NET? So do I try to sort of manually create classes, model languages that correspond and keep it in sync, or what do I do? So what we did here, we've actually had sort of this support in a slightly different form for a bunch of years. We tried protobufs for a while, but the .NET really didn't like that, didn't perform very well. So we came up with our own format. It's essentially a very compact binary storage format with some metadata on top of it. The APIs on all the languages know how to work with that format. And it has a really, really nice side effect. Even if you're not using anything but Java, let's say, it still gives you some really nice benefits, like a dynamic schema. So I now have the ability to essentially modify those objects that are in the grid at any time. You think about sort of a generic object with arbitrary getters inside. If you set a property that has been there before, great. If you set a property that hasn't been that before, we'll just add it. If you try to get a property that's there, great. Get a property that's not there, we return null, right? So it doesn't error, you don't worry about class versioning or any of that kind of stuff. And it performs very, very well. In fact, we found that it actually performs beyond our expectations. The other big feature that we added recently was the concept of grid managed services. We essentially gave official support to a pattern that we saw a lot of our customers doing, which is, I want to run something in the grid, but I only want one instance of it to run. And you could write some code and kind of put that logic in there and make it happen. But now we just have a way to declare it in code. So you say, I want a process to always be running somewhere. I don't care where, but I want one instance of it. Or you can say, I want one instance on every box. There's a few other configurations. So basically, you tell us what you're trying to do, we make sure that it happens. Right? So we spin it up here. If that box goes down, it goes up one other place. You have those guarantees without having to write any code to make it happen. I also promised to point out the difference between enterprise and open source. Open source has all the functionality that we just talked about, first of all, with the exception of Visor, which is right here. So Visor is an enterprise-only piece. But it is included in our open source download in a trial form, so you can try it out just on your local box. But all the other stuff we talked about in open source is there. So this is huge, right? Nobody else provides off-use support in open source. And we don't restrict how you can deploy it. But we do add some things to enterprise that we think, if you're going to go into production and it's an important application to you, these are the kinds of things you might care about. So the Visor management, the ability to back up data that's in memory to look at this, to replicate data between different grids and different data centers, protection against split brain or network segmentation is in the enterprise product. There's some security features you can authenticate grid nodes. There's an ability to upgrade live, right, to rolling production updates. Take out, they have a grid of 50, right? I take out a couple of boxes on the old version, I put them in the new version, I put them back in, and then I roll through the rest. What you'd want to be able to do, right? You're running two different versions of the software at the same time, which is key to making it happen. So we support that in enterprise, we don't in open source. And then, of course, last but not least is our support, right? So we're focused on service and support of enterprise customers. When you become an enterprise customer, you have unlimited tickets, any of the emails, web meetings, phone calls, whatever you need to do to resolve your issues. If you run into something really unique and you need a patch, we'll turn that around very quickly for enterprise customers as well. So that kind of sums all that up. If you have more specific questions, please feel free to come up and see me after, and feel free to follow the conversation if you're on Twitter. If you don't have any other burning questions, I think we're almost on time. We're just a minute over, and I should relinquish the stage, and I encourage you to come up and talk to Twitter and myself afterwards. Things you'd like to talk about, for me as a technical guy, understanding your use cases is the fun part, so please feel free.
Thanks, Mark, for a great presentation. Now have Dave from MapR come and give us a talk about NoSQL and Hadoop. Please give a warm welcome to Dave.
Thank you so much.
Great. Hi, everyone. My name is Dale Kim from MapR. Thank you for joining me tonight, and thank you to Subash for setting this up. So I think it was his responsibility for making sure you guys came. I think it's incumbent upon me to make sure that you guys want to stay throughout the whole presentation. So my lame attempt to try to get you to do that is to bring some tchotchkes. So you might have seen some books up front. New Buyer's Guide, Time Series Database book by our Chief Application Architect, some bottle openers, and a USB card that has the MapR sandbox on it. So if you install it onto your computer, then you can run with either VirtualBox or VMware a single node, got it right there. Yeah, mostly the USB thing, but the sandbox on it is pretty cool stuff. Yeah, you can download it from a website, but if you start that up, there are examples, tutorials, and user interfaces to help you get started with the do if you're interested. Also, I wanted to ask some questions along the way and give out some MapR t-shirts. So if you're into that, then you can hand out some of those. Nice, attractive, red MapR branded t-shirt. Unfortunately, I don't have medium, but hopefully you have somebody who can wear it into the video. Rush, does this sound like an interesting thing to you? Okay, well, here you go then. I didn't say the questions were going to be hard, so let's get started. So, number of topics we want to talk about. Give a brief overview, maybe a summary or a review for a lot of big data topics. Talk about the in-Hadoop advantage. So you might have not heard of the term in-Hadoop, but that's the term that we're trying to popularize to talk about the notion of new technologies running within the context of Hadoop in the same cluster. Also want to talk about NoSQL on Hadoop in action. So what are some of the Hadoop use cases that blend together NoSQL and Hadoop? Want to talk about some other in-Hadoop technologies that are available. And finally, want to talk about how SQL fits into the world of NoSQL. So you've probably heard the story before, big data meetup. So you know the whole story about big data. You know the definition, volume, velocity, variety, and usually some weird fourth component that nobody really knows about. But usually stick to the top three. So my question to you is, with all the different definitions you might have heard over the years, what's the definition of big data? Does anyone want to offer a definition of big data that I might have never heard? No takers. I would have accepted who cares as an example, because it doesn't really matter. The issue is not about what big data actually is, but some of the challenges you might face. And one of the challenges is if your data grows beyond some predictable bounds, then your traditional systems might be overwhelmed by them, and maybe not. There are some environments and some customers that we've talked to where they said, yes, we can handle the new volumes and the new scale with our existing systems. It just would have been cost prohibitive. So we want to look at some of the new technologies to be able to handle that new scale, the new volume. So if you look at some of the dimensions in which we look at big data, if you look at data, volume, velocity, you probably know the story, you've probably seen this before. The notion of scale up worked really well for things like data warehouses and relational database technologies. Buy bigger boxes if your data is very predictable. And if there's data variety, then you tend to spend a lot of effort on the ETL and the data modeling as that data grows. You contrast that to some of the newer technologies where it's more of a commodity hardware, scale out, linear scaling type of model. So as your data set or your user groups grow, you add more machines. And then when it comes to like data variety, you can use Hadoop and NoSQL in conjunction. So in fact, you can think of both NoSQL and Hadoop as two of the top technologies used for big data today. Sometimes people even think of those terms as being synonymous with big data. And so when you think about solving big data challenges, you often don't think of Hadoop or NoSQL, one or the other. You often think about them together, especially from a high-level company perspective. In your particular department, you may be focused more on the updates, read-write capabilities, the operations, or you might be on the analytics side where we talk more about the batch grouping, the batch aggregations that you run for hours or days at a time. But in the big picture, you're handling big data with both Hadoop and NoSQL. And of course, some of the newer challenges that people are facing and trying to solve are things around reliability, disaster recovery, interoperating with your existing systems, performance. So a lot of those things are being handled quite well on the NoSQL side. Some of the Hadoop vendors are relatively new to that. MapR is where we differentiate ourselves in terms of like a lot of the enterprise-grade features that you would expect in your Oracle or your other data warehouse environments. So just to quickly review, you might know NoSQL to be simply a class of databases that handle scale out very well, as well as flexible data stores. Does anyone have any other thoughts about what NoSQL means, what it entails? That is a very good way to put it, yeah. That's worth a shirt. Yeah, there's this notion of schemaless. And put it another way, I don't have to bother my DBA, or I don't have to talk to them, because nobody likes talking with DBAs, right? So you don't have to talk with them. And that's a good way of describing it. And so Hadoop, on the other hand, is a distributed platform, scales out, it's good for storing large files, and it's good for doing what I like to call divide and conquer. So break up work in smaller chunks, and then bring that all together. But before we continue, let's take a look at, oh, I'm sorry. So there's definitions, NoSQL and Hadoop. But before we continue, let's take a look at one of the big data pioneers, Google. So they first started off with the Google file system and the notion of MapReduce. And that was used initially for the PageRank system. So not necessarily for indexing or searching web pages, but for the indexing and for the analysis of what pages were more important. And so the notion of MapReduce was a great thing because it didn't have to return right away. You could spread it across thousands of commodity servers. And in fact, you might remember that Google was one of the first pioneers in pushing this notion of scale-out technologies. And it's a bit different than a lot of the other companies at the time who are using huge Sun Microsystems machines to run their web businesses. Soon after that, Google created Bigtable, so essentially the real-time database system built on top of the Google file system. And in fact, that's where our founder and CTO, MC Srivas, came from. He led that team to incorporate this notion of operations on top of analytics. And as a result of the operational component, the Bigtable component, they were able to build many more applications on top of what they already had with the PageRank. Things like Google+, things like their messaging, like mail, and anything that requires some type of real-time user interaction. So when you contrast the PageRank system with all the operational things, that kind of implies two different data sets. So if you're an analytics guy, you might, or let's start with the operations guy. If you're a database guy, and I use the term guy in a very gender neutral way. If you're a database guy, then you might be familiar with all the updates, interactive, real-time, the cool stuff that you do with users. And at some point you huck that data over the fence, and then somebody else deals with all the large-scale analytics, bring some of that information back into your system so you can incorporate that as part of your interactive system. If you're an analytics person, then you know that the data comes from somewhere else. You don't create the data. You get it from somewhere else and do a whole bunch of processing on it and perhaps huck it back over onto the operational side. So the question is the data really different? You think of it in different terms, but is it really different? And it's more a difference in terms of time, in terms of how it's processed. So if you consider that, we can think of a typical architecture as looking like this. You have your one cluster for the operational or database side. You have another cluster for the analytical side. And everybody's happy. And you work on it in your own individual silo. It's not necessarily a bad thing. This is the way it's accepted, and this is the way you do it. And in fact, a lot of these systems often come up, a lot of these silos come up as a result of some business-specific need. So you build an application on some very cool NoSQL technology, you got your application up and running, and at some point somebody says, hey, we need that data for analysis. So you copy it over the wire to them, and they do some analytics. And you just go through the batch import and export. And again, you can do all these cool things like churn analysis, customer 360 dashboards. You can have your mobile access and web applications working in parallel. But what I'm seeing and what I'm claiming that we'll see more and more of is the integration of these two technologies working together as one. And that's where the notion of an in-Hadoop database will arise. And so now you have a single cluster that simplifies your entire architecture and creates a lot of additional operational efficiency by having all your data in a single location. So no longer do you have to do duplication, data copying, redundancy of functionality, redundancy of effort. You have it all in the same cluster. You have the information coming in. You do all the real-time interactions, analytics on the same time. You might have some resource separation being handled by that cluster, but it is all still the same cluster, so there isn't a lot of the movement and copying that you would expect from your typical architecture. But in addition to that, there are also some more real-time aspects that can be had. So rather than loading data, maybe terabytes or petabytes of data onto your analytics system, you have it available for analytics on the spot. So you can do more real-time things like personalization and ad matching, or a lot of use cases that some of the more advanced Hadoop and NoSQL deployments are pursuing. So just to summarize, if you think of the separate Hadoop and database cluster, again, you have a lot of challenges that add a lot of inefficiencies when you're copying big data across the wire. Now, if you're talking about gigabytes of data per day, then that's not going to be a big deal, and this isn't an issue that pains you. But when we talk to customers, they would talk about copying many terabytes of data over the wire. And sometimes it would be so slow that it would spread over onto the next day, so they wouldn't be able to catch up. So they needed a way to be able to accommodate that. And one simple way to do that is by having that consolidated cluster that has both functionality and handles both spectrums, or both ends of the spectrum of workloads. By having that consolidated deployment, and so this isn't just a MapR story. I think this is going to be a technology story in the coming years where more and more technologies are going to be Hadoop focused. If you have a consolidated deployment, you'll have a lot more capabilities and you gain a lot of operational efficiencies. Now, if you're a developer, a lot of this won't matter to you because you have your own responsibilities, your own goals about how to accommodate end users. But if you're thinking it from a bigger picture, there are some additional things that you might not have thought of, like the real-time aspect, that'll be very valuable. And if you're an enterprise architect, you'll probably say, yeah, this is the type of model I want. These are the type of challenges I want to avoid. I don't want to have to deal with a lot of the overhead of moving data. Any questions so far? Okay. How about a good question so I can hand out a good question for me so I can hand out another t-shirt? Okay, think about that.
I don't know if it's a good one, but
All right.
when you're dealing with this combination now of your sort of NoSQL access and your batch processing there, is that just kind of putting them together in the same server so they're close together on the same machine, or you're saying common storage format as well? So transform that, you're storing it once, using it in two different ways.
Well, with Hadoop, you could have it in the same node. You can have it on different servers with the same cluster. There might be a different storage format, but like in Hadoop, you might have it in an H-based server that is still accessible by MapReduce. So it'll be a different format, but still accessible by the same tools. So you essentially have that consolidation still by just using the same Hadoop ecosystem tools. That was a good question. Any other questions? So let me focus on a little bit deeper the technology aspect, or maybe a more specific angle in terms of why in Hadoop databases matter. Let's take a look at it from purely a storage perspective. So if you guys are into databases, then you'll know that databases want direct storage. That's the best implementation for any type of database. You get the direct access speed. And from a business standpoint, it tends to be lower cost. But certainly there's more management associated with it, and a lot of administration is incumbent upon the database system itself. But this is what databases do want. They want that direct storage on each node. On the other hand, you might have a corporate policy that says they want to use a large SAN or NAS because of all the great enterprise-grade features that it has and all the scalability features. But they are complex, and they are expensive. And they're expensive because they're worth it. You get a lot of value out of them. But there are some challenges with running them with databases, whether they're relational databases or NoSQL databases. In fact, one company that I used to work for, a NoSQL company, was a high-performance NoSQL database. And at one of our customers, they were running on a SAN because that was the corporate policy. Unfortunately, the customer under-provisioned the I/O into the SAN so that our system at times would be overloading the disk and then thinking that something failed. And then when one node failed, the others would have to take over for it. And then something else would happen with the I/O, and then another node would fail, and just cascaded from there. And so the customer was really angry about how come our system was so unreliable. And so it turned out just the complexity of having a SAN with another complex system on top of it running together resulted in that problem. So we tried to convince them to move over to local disk, which was against our policy. But they came up with some compromise around increasing more I/O simply for that particular system. But it adds a lot of complexity when you're dealing with databases that, again, want that high speed. So one area where I think Hadoop is going to help quite a bit is allowing all the benefits of direct access, so the low-cost disks as well as the high-speed direct access. But because the disks within a Hadoop environment all network together, you get a lot of benefits in terms of the scalability, in terms of potential around administration. And so there's a lot of opportunities for scaling. Certainly the lower cost is going to be important, easy capacity expansion, and even copying of data across the different nodes is going to be a lot more simple than if you had completely separate nodes running databases in a clustered environment. Any questions on that? And so, of course, I'll talk about some more examples of technologies that are using this architecture as a way to benefit beyond what they're doing right now. So, has anyone heard of the Lambda architecture? Good. I'd give you another shirt for raising your hand. But so when I talk about Lambda architecture, typically a lot of people have heard about it, but it's a pretty interesting concept. So you can look at it, look it up on the lambda-architecture.net site, which is essentially a bunch of guys that like evangelizing the value of the Lambda architecture. It was actually created by a guy that worked at Backtite, now owned by Twitter, and a guy by the name of Nathan Mars. And what the point of the Lambda architecture is to undo some of the complexity of NoSQL systems or distributed systems. So can anyone tell me what the CAP theorem is? No takers? Taker.
Capacity, availability, basically, I can't remember the last particularly, maybe, but it's basically referring to kind of the trade-off that you can't ever really have 100% consistency in some certain depending on circumstances, right?
Yeah, exactly. I can be sure, can I?
Yeah, I remember.
Okay. So CAP stands for consistency, availability, and partition tolerance. And basically what it's saying is that there is a compromise that you have to make when you're deploying a distributed system. And this was a theorem created by Professor Eric Brewer at UC Berkeley. And what it's basically saying is that you can expect some compromise, some trade-off. And so some systems will trade off in terms of consistency, like Cassandra is an AP system, meaning that it focuses on availability. So it'll always give you an answer, whether the answer is up to date or not. And Matt discussed this a little bit. There's also the notion of giving up availability or focusing on consistency. Something like HBase is very consistent. So I think I screwed up that description, but I think you get the point. Either consistency or availability is what you get. So what the Lambda architecture is saying is the hardest thing about a distributed system is that you're changing data. And as basic as that sounds, that really is true, because in a distributed system, you have to have replicas of your data across multiple nodes. And when you have replicas, you have to keep them in sync with your primary node. And that's the hard part. And in fact, as part of the Lambda architecture, when Nathan Mars blogged about it, so if you want to read his entire blog, look up how to beat the CAP theorem. And so he talks about that a lot. And so what he's saying is, what if your data is unchangeable? And he also says, isn't all data, in fact, unchanging? So for example, I'm standing here right now, and he's saying that if I move here, what changed? Most of you would say, well, you changed your position. What he would say, you simply added a new data point. So at some point in time, I was standing there. Now, in this new point in time, I'm standing here. So that's a new data point that you can add to the system. If you follow that model, then you can use Hadoop and NoSQL to model it very well. And so with this Lambda architecture, what it's saying is that there are a few layers. There's a batch layer, a speed layer, and then a serving layer. The batch layer simply says, let's take in all of your data, potentially, Internet of Things sensor data, or a dump from your Oracle or data warehouse into Hadoop as it lands, keep it static, but then run some type of batch process on it so that you get some views, like through Hive, to search on it. And so that goes up to some certain point in time. And because that's never changing, if you make an error in your code and you need to rewrite it, then you can, and just use that canonical immutable data to create that new view. Or if there are different types of queries you want to run, you can do the same thing. So that's the batch layer that you run behind the scenes over some long period of data. The speed layer sort of incorporates the NoSQL component, where you can stream in all that recent data, and there might be some changes to that, but you're limiting the complexity, in other words, the updates and reads and writes, to that speed layer to a smaller window of time. And then when you combine that small window of time of the complex part with the batch part, then you get the merged view. So now you get a complete view of all your data. You've limited the complexity of the updates, reads and writes all together to the speed layer, but then you have that canonical immutable view. So if you read the blog that Nathan had put together, How to Beat the CAP Theorem, it takes probably a little bit of time to fully digest what's going on, but this is a good model for any type of streaming application that you might have. So let's move on after that. Just know that that's a potential topic that you can research. Then the notion of enterprise data hub is something that's increasingly popular on Hadoop. So it's essentially a central hub where you collect data from a number of silos so that you have this central view of all your data. You know, you can use it for things like customer 360 degree views and consolidating data silos across your organization. So there are a couple key points here. On the left, you see loading different data sources into your enterprise data hub driven by Hadoop. You have this notion of ETL within Hadoop, so you can run a number of processes to clean up the data, to enrich it by combining different data sources together. There's a notion of offloading and enrichment, so you can copy data from your data warehouse into Hadoop, do some processing, copy it back in, or vice versa. You can load data into Hadoop, do some processing, load it to your data warehouse. And then there's the analysis portion, so that you can use some of your standard tools or some of the new Hadoop tools for processing the data and analyzing the data. And so you'll hear about the story of an enterprise data hub or a data lake. You might also hear the terms data swamp or data landfill. There's a lot of angst in terms of like what you could potentially do and what you could potentially screw up when you have such an environment. But there's a lot of documented use cases of customers being very successful with such an implementation. But just want to talk about a few Hadoop implementations. And so I used to be pretty cynical about any company that says we have Cisco as a customer, because everyone had Cisco as a customer. But now that I'm MapR, I can't be as snarky because Cisco is a huge customer of MapR as well as a huge partner. So I try to be very positive about the notion that they're a customer of ours. So they actually run many Hadoop installations. And most of them are MapR, but with any big successful company, you're going to have a variety of technologies available in there. But some of the big technology implementations on MapR include an enterprise data hub or a data lake. So the central IT group incorporates data from a number of sources. And one of their first big wins is being able to identify $40 million of incremental revenue for their partner services department as a result of having this complete view of data in a central location. So that necessarily incorporates flat files, necessarily incorporates read-write data in databases. Having all those workloads available in their enterprise data hub allow them to do deep analytics and find where those opportunities work. Another environment within Cisco is their MSSP division, so the managed security service provider. They essentially analyze network data on behalf of their customers. And when you analyze network data, there's a lot of pattern matching, there's a lot of pattern identification, a lot of anomaly detection. So it's not a matter of just looking for blips. You want to study data over many periods or long periods of time. See what the anomalies are, see what the normal behavior is, and when you see specific anomalies, you know there might be an extra risk, and you want to be able to do that in real time so that you can notify your customers. So that's another implementation of using Hadoop to be able to detect potential threats from a network standpoint. Exactly takes the NoSQL and Hadoop model a little bit differently in that they use Hadoop for a lot of the aggregations and the large-scale batch processing, and they use NoSQL as more of a reporting system. So they use Oracle for their interactive web application for all the input and output with their customers, dump all that information into Hadoop, do a lot of aggregations, and build it in a way similar to the batch layer in the Lambda architecture. They do a lot of aggregations to prepare it to be presentable and reportable by end users. And so they load it into the NoSQL database, and now they have an interface on the web system so that users can click various buttons and run various types of reports simply by running filters. And they need very fast response time. They couldn't do that with Hadoop alone through Hive or through MapR for that matter. So by loading it into NoSQL, they're now able to have the seamless single cluster of all the data they dumped from Oracle and have quick operational reporting. Now, a big telecommunications company collects set-top box data and can analyze that to understand what their customers' preferences are when it comes to not only shows, but also commercials. So they can better target commercials to users based on their behavior, whether they pause on a commercial, whether they fast forward it or change channel. And so certainly you can't just look at 2 or 3 months of worth of data. You need to look at years of data. So they're able to store this huge volume of data and think about all the clicks across their millions of households they might support, stored in Hadoop, running within NoSQL database to do a lot of fast calculations around the pattern matching and pattern identification. And so again, it's this notion of being operationally efficient by having that single cluster. And then last but not least, a financial services firm wanted to build a fraud detection system that essentially captured all their user transaction information into a single repository. And when they had that, they realized that with all the behavior that they're understanding about their users, not only could they understand what deviates from normal behavior from an individual and aggregate layer, but also they could see what their preferences are in terms of what kind of offers are available to their customers. So it started off as a fraud detection system for user transactions, but then morphed into being able to identify offers. So not only about reducing costs, but also adding additional incremental revenue. So that's one of the trends that you'll see in terms of the multi-use case deployments with Hadoop as a result of combining it directly with NoSQL. So that's mostly what I want to talk about. Just want to have a quick segue, talk a little bit about MapR. MapR, of course, is a NoSQL and Hadoop provider. We've been recently written up in Forrester research reports as having the top-ranked book Hadoop and NoSQL distribution as a result of all the capabilities that we've provided. So MapR is notorious for spending a lot of time building a solid technology versus some of the other competitors who have gotten that head start. So while we were in stealth mode for many years, spending a lot of time building out the low-level architecture, I think we have an opportunity to show what we have in the market and how it differentiates from the other Hadoop distributors. Just want to talk about briefly, we provide all the same projects that all the other Hadoop providers provide. So you run an application on somebody else, you can run it in MapR and vice versa. It's all the same code, particularly with the open source community projects built on top. So I'm not going to beat you to death on it, but MapRDB is our NoSQL solution integrated with Hadoop. And so this is the high performance, enterprise grade NoSQL solution built in so that you can have that operationally efficient single cluster for your multiple workload environments. One of the interesting things about MapRDB as a result of being embedded within Hadoop is that it eliminates a lot of the layers that you would see from something like HBase, where HBase is running on top of HDFS, has JVMs attached to them, running on top of the Linux file system, whereas MapRDB is all consolidated within the MapR data platform, runs directly on disks. So it follows the Oracle model of talking to raw disks. So we have our own file system that handles that direct I/O and does all the caching, designed for handling multiple workloads. It's not more of a generic operating system like you would find with Linux, it tends to be good for desktop work. It's designed for handling a wide variety of workloads because we control all the I/O. And that's one of the big architectural differences from what we have versus some of the other databases. And one thing that we like talking about, when you're talking about NoSQL databases, one of the challenges they face is this notion of compaction. So at some point, there's some defragmentation process going on that essentially rewrites some of the contents on disks so that it can continue to run fast. But during that time, there's a lot of I/O. So you encounter what's known as I/O storms, where there's a lot of reading and writing and trying to clean up. And because we control the file system and direct I/O to the disk, we can eliminate a lot of those delays. And so if you look at this chart, you see the blue represents the response time of MapRDB with varied loads, whereas on HBase, you'll see the yellow spikes as a result of this compaction or defragmentation work. And so anytime you have like a web application where you want that consistent fast response time, that's where this type of benchmark would show it to be beneficial. So let's quickly talk about some other Hadoop databases. So certainly you've probably heard about Apache HBase. That is the Hadoop database based on Bigtable, built on Hadoop. So that's the standard that everyone goes by. And in fact, MapRDB uses the same API as HBase. So if you know how to program in HBase, you know how to program in MapRDB. Has anyone heard of a Cumulo? Apache Cumulo? Worth a shirt. Who built a Cumulo? That's right. So that's one of the fascinating things about the Cumulo project. So as much as the NSA has gotten criticism in the past few years about what they've been doing, even before that, they got criticism for writing their own software. So some of the folks in the NSA wrote a Cumulo as a result of some of the systems out there not being sufficient for security level protection. And I always like to joke that all of that information that the NSA has been collecting over the past few years is stored in the Cumulo database. Now, I don't know that for sure, but I like to think that. And in fact, some of the folks from Accumulo started their own company called Squirrel, based in Boston, I believe, SQRRL. So Squirrel is the company that provides support for the Accumulo database. Splice Machine does something really interesting. They're based in San Francisco. They've built a database on top of Apache HBase, so on top of Hadoop. But they've built a relational database on top of a NoSQL foundation. So if you're looking to do relational type of work, along with ACID transactions, the full rigid schemas and all the goodness that you get in a relational database, Splice Machine has built that using the infrastructure on Hadoop. And in fact, Splice Machine is so bold as to say they compete against Oracle. They expect to replace a lot of Oracle installations as a result of being able to have a scale out, low cost, very efficient environment. And then MarkLogic is doing something a little bit different in terms of the in-Hadoop model. So they're not focusing so much on some of the benefits of the scalability. They handle a lot of that good stuff already. But they are a premium price solution. And so one thing that they wanted to do is be able to let their customers focus on particular data sets. And by storing their data sets on Hadoop, they can now swap out different tiers of data depending on what they're trying to search for. So think of it as a tiered approach, a tiered data approach versus anything else with what they're trying to do. And certainly there's some data warehouses built on Hadoop. HP Vertica is interesting for us because they built some of it, or they could run it on top of a Hadoop or MapR cluster. And in fact, some of our competitors come to us at trade shows and ask us how we're able to do that. And we don't have a good answer for them because it has a lot to do with some of the innovations we've built. So there's not a lot that we can share there that would enable them. But the important part I'm trying to mention is that the fact that they're even asking about that shows that this sounds like a valuable thing, being able to run other technologies within a Hadoop environment. And that's why I think that a lot of technology companies are really thinking about how to incorporate it into the Hadoop world. And of course, Pivotal has Hawk running on top of Pivotal HD. Pivotal also has a NoSQL database called Gemfire XD or something like that. I don't really know a lot about that, but it sounds like it's a pretty compelling in-Hadoop database as well. And of course, whenever you start talking about Hadoop, whenever you start talking about NoSQL, there are all kinds of topics open up. So I have to talk about some of the SQL query engines, and it's always funny whenever you talk about SQL query engines on Hadoop with analysts because they're all sick of it because they think they're all the same, but they're really not. And there are a lot of nuanced differences between each of the SQL query engines on Hadoop, and I probably can't tell you all of them, but I want to tell you a little bit about the thing that MapR is the most close to. But I'll get back to that soon. So in-memory processing is something really important. Has anyone heard of a company called GridGain? Okay, so you heard about GridGain. Apache Spark, you might be familiar with, technology that focuses on in-memory as well as just another execution engine that can be run on a variety of persistent stores. Another interesting technology that MapR recently talked to, it's a fairly new company called HammerTech. So HAMRTECH.com. And so they're kind of an in-memory processing engine as well, and they're relatively new. So they have about 60 customers in their beta program right now, and they focus on a single model for batch interactive real-time streaming analytics. So a similar story to Apache Spark. They claim to have 9 times performance over Apache Spark, so it might be something worth all of you checking out. Again, hammertech.com. Certainly. Max said a lot of interesting things about what GridGain could provide as well within a Hadoop context. So here are some of the SQL on Hadoop engines that are available. So you've got, okay, let me quiz someone else. So who knows where Presto came from? How about if I give you a ball? Whoops, sorry. That's right. And so the oddity about that, about Presto coming from Facebook, is that they're not a vendor. They just created technology. And so you kind of wonder what's going to happen. And I think that somebody's probably going to pick it up and then run with it as the commercial vendor for Presto. How about Phoenix? Does anyone know where Phoenix comes from? Your ecosystem. Yeah, Phoenix comes from Salesforce. So again, they didn't see a solution out there, so they built one themselves. Released it open source. And I think a lot of these technologies will continue in that model. It won't necessarily be the vendors, the Hadoop vendors, or even commercial providers within this space that will be building these technologies. It'll be companies that see a need, don't see anything else out there that fits their need. They'll build it, release it to open source, and then who knows what will happen. But hopefully, some of these technologies will win and emerge as the right choice. But to tell you, like I mentioned earlier, there are some nuances between the different technologies. Some focused on speed, some focused on SQL compatibility, some are on Hive compatibility. Apache Drill is the technology that MapR initiated. MapR doesn't own it. It's essentially an Apache project, so it's owned by the community. But we did lead the effort, and so one of the initiatives that was important as part of Apache Drill was this notion of searching over nested and hierarchical data. So that's going to be Apache Drill's big directive. How to be able to search over things like JSON. And with all the interest that we've been hearing about in terms of querying with your Tableau or MicroStrategy tools over the new types of data sources like JSON, how would you handle that? Certainly a lot of technologies today can do that, but there's some ETL or some table creation required up front. And so what we're trying to say is going back to the story of not having to talk to your DBA. That's what Drill does. It allows you to explore the data without IT intervention and just let the tool allow you to have self-exploration of that data. So my last slide is a picture of my presentation at the Orange County Big Data Meetup. And so this is what I call, it's an internet meme that I try to start, what I call a staging, taking a picture of the audience from the stage. And if you take a look at that, you'll probably see something peculiar. Now, I asked the audience to look like they were asleep. So I showed that to my colleagues back at the office, and most of them didn't notice that. I guess I kind of expected everyone to look like that when I was talking. I don't know. But I just thought I'd want to show that. So that's in Hadoop databases in a nutshell. So I talked about the architectures that are available as a result of consolidating these two technologies, some of the technologies that are emerging. I really do think that some of the popular NoSQL databases out there right now connect via connectors or maybe by Hadoop tools like Scoop and Flume, but I think they're going to be emerging to the point where they are built on top of Hadoop. Take advantage of that scalability, take advantage of the possibilities for immutable data stored in Hadoop and then processed within a NoSQL environment. That's my opinion, and hopefully, more technologies will come that way so that we will have more simplicity around some of the deployments that are going on. Any questions? All right, well then, thank you very much, everyone.
So, once again, I want to thank Mac and Dale for presenting today, and hope to see you next week at the Spark meetup. Thanks once again for coming.
Wait. The big raffle.
The raffle.
I'm one of these guys that takes your name and tells you we're going to raffle, you never hear about it. So, the way we do it is when everybody registers in the front, we generate an Excel spreadsheet. Everybody's familiar with random.org. Put the numbers in, bam, spit somebody out. Forgive me for the name now, Ahmed Azazida. Nobody, huh? I was close. So let me go back and generate another number. Okay, let's see there. How about Dave Sullivan?
Right here.
There you are. Thanks, everybody.
A lot of stuff. This is really cool. Awesome. All right. This is yeah, $10 in class. Really cool. It's not so good. I'm sure.